second course of this day that regards the use of in-situ sensing technology. In the framework of the HERACLES project, sorry. In the framework of the HERACLES project, we use the several in-situ sensing technology for study for study structure and soil, and in particular in this presentation I want to focus the attention on the use of the GPR. So the outline of this presentation is just to give you an idea what we speak about when we speak of a sensing technique, electromagnetic sensing technique. Then I go in depth on the GPR working principle, and also just give you some idea of what are the basic working principle, the futures of a GPR system, and also what are the products of the obtaining in GPR in the framework of the HERACLES project. Well, just to say that the GPR is an abstract technology to denote an electromagnetic sense technique working in the microwave frequency range and working in sight. That means directly in contact with the area that we want to investigate. The GPR works in microwave range, so the resolution that we can have is about of some centimeters, and also it depends on the specific frequency at which we are working, or frequency range to be more precise, at which we are working. Just to give an idea, we are always use electromagnetic sensing. First of all, with our eyes that are a natural, let me say, electromagnetic sensing technology that works in the optical frequency. This is a passive and surface imaging tools. Passive because it exploits the sun radiation to observe what are the objects that surround us, and also a surface imaging technique because it allows us just to observe what is in the surface. For instance, with our eyes, we cannot see what is under foliage, what is neglected by the presence of vegetation. Another common sensing technology is X-ray. Always we work in the electromagnetic spectrum. Now we are working at very high frequency, more or less at 10 over 17, 10 over 19 Hertz. This is a very common imaging technique exploited a lot for security purpose, but also in medicine. And in this case, we have an active and subsurface imaging technique. Active because we have a not natural source to generate the X-ray, and also it is a subsurface imaging because it allows us to see what is there are, for instance, a luggage. So it allows us to see the state of our bone, for instance, when we have a fracture. Another also quite common technique is the infrared. In that case, this imaging technique can work as active or passive technique. It's active when it exploits the artificial source, like in this picture, where we have that a lamp radiates on a surface to increase its temperature, or also it can be a passive technology when we exploit the natural temperature of, for instance, of our body. Okay, the ground penetrating radar is a active subsurface imaging technique. It's active because it exploits the antennas and a transmitter to radiate, to generate an electromagnetic probing signal, a microwave probing signal, and also is a subsurface technique because it allows to see, for instance, what happens under the ground, or it's what is the internal structure of a wall. The basic principle of a GPR is the same of a common radar. We have a transmitting antennas that radiates a microwave signal. We have when the signal sector on an object, an echo is reflected and received by a receiving antenna. By knowing the characteristics of the medium where we have the propagation, we are able to obtain information about, for instance, the distance of the object, but also on the features of the object. The difference is that while a radar works in air, a GPR works in presence of a medium that is, for instance, a soil or a concrete. This implies some difficulties. First of all, when we are in air, we know exactly the behavior of the transmitting and the receiving antenna. We also know exactly the characteristics of the medium where the propagation occurs. And also with the radar, we are commonly interested to detect objects that are quite far and also are quite large. Their size is of some of 10 on 20 meters. When we work with the georadar, the first propagation is that the propagation occurs in the intermedium whose electromagnetic characteristics are not exactly known. Moreover, we are often interested to detect objects that are near to the antenna, and also object whose size is of a few centimeters on the less. What we are able, what we need to take into account that when we use a georadar is that what we can do is some electromagnetic variation with respect of the medium where the propagation occurs. So it is important to take into account that from an electromagnetic point of view, the materials are characterized by some properties that are common: the permittivity, the electric permittivity, the electric conductivity, and of our interest are non-magnetic materials, and also we are mainly interested to the electric materials that are not metallic materials. So the most important properties that we need to take into account is that the materials are characterized according to their permittivity, and the permittivity of the materials can change depending on the composition of the materials, depending on its water content, and so on. So briefly, we can say that we can classify the material by taking into account their dielectric permittivity or dielectric constant, by taking into account that the most simple materials is the air, whose dielectric constant is 1 and the conductivity is 0. In the opposite side of in this classification, there is water, that is the material with the highest dielectric constant, and in the middle there are more or less all the materials whose characteristics, as I said, can change depending on the water content. So for instance, the same material can present completely different permittivity and electrical conductivity depending on its water content. What we can see with the GPR there is the variation of the dielectric constant or dielectric permittivity with the respect of the medium that we are taking as a background or as a reference medium. So for instance, if we have a wet soil into a dry soil, we can discriminate, we can detect the presence of the wet soil because we have a difference of the electromagnetic permittivity. Just to present as is done a GPR, we have a transmitting and receiving antenna that are usually shielded into a box. We have an encoder that allows to take the exact position of the antenna during the acquisition. There is of course a battery to provide power to the system, a unit control, and also the laptop where there are the software necessary to control the GPR, but also to storage and process the data. This is a very schematic block. As I said, the transmitting antenna transmits a signal that is received by a receiving antenna, stored into memory, in local memory, and then the data are processed to provide the results. Okay, also briefly, there are two main kinds of GPR system, the impulse and continuous waves GPR system. We use mainly impulse GPR, or better in the HERACLES project we have used an impulse GPR system, that is a system that works in a time domain by transmitting a pulsed signal, and then it receives a signal that is a function of the time. Usually, another important thing is that when the GPR is designed, or the choice of a GPR system is dictated by some general features that are the requirement to have a flexible and simple to use device. The device also needs to be portable and possibly with a low cost. And and also to capable to provide accurate results in a few minutes by keeping low the measurement time. This is why there are several kinds of systems. We have systems that are used by hand, but also systems that can be used by mounted on a car or on an aircraft. Regarding the accuracy of the results, of course, this depends on the sensitivity of the radar, that is the capability to detect weak targets, by its measurement capability, that is the ability to estimate with accuracy the radar target distance, and of course the resolution, that is the range and cross-range resolution, and it depends on the frequency at which we are working, but also on the kind of material that we are investigating. Just to give you an idea, since we have an instrumentation that allows us to obtain in a non-invasive way information on some things that cannot be inspected by eyes, this kind of instrumentation is used in a lot of applicative scenarios. The classical one are geology and geophysics, in which the GPR is used, for instance, for soil characterization, for hydrology surveys, but also in glaciology. And information that one can try to obtain are very different. For instance, the identification of soil stratigraphy, but also the detection of cavity on the cracks, the identification of the water table, but also the monitoring into the space and in the temporal scale, the water content, for instance, of the ground. Also in a typical applicative field is the glaciology, for the ice characterization, the determination of the bedrock, and so on. And this kind of information are very useful, for instance, to obtain information for the climate change, both in global scale and also for the local scale, because the change of the glacier morphology has an impact of the climate of the Earth, but also of the local climate, and also on the modification of the terrain. Other applicative context that is close to the HERACLES project is the survey of cultural heritage. That means both archaeology, GPR is used a lot to map ancient ruins which are before an excavation, just to give an indication of the most interesting area where it is interesting to concentrate the archaeological excavation, but also is used in, let me say, risk archaeology. That means to detect risk factors that can affect the structural integrity of a building, historical buildings, or ancient building or structure. Other applicative context is the civil engineering. Just I can skip this slide. And also the security, but also in this case we can skip and move to the what kind of data the GPR can provide. As I said, we have an antenna that transmits an impulse when the signal strikes on the target. There is a reflected signal that is connected by by receiving antenna. So we have for each position of the antenna, transmitting and receiving antenna, let me say the antenna system, we collect a waveform that is that is a function of the time, present a peak in correspondence a peak that come back, and the time in which the peak appears depend on the mutual distance between the antenna system and the target. So if we have, for instance, a point-like target, that means a target whose size is less than the wavelength or comparable with the wavelength, we have that the image that we have of this target is an hyperbola, like in this picture, in the picture on the right and in the bottom side. So we don't have a picture of the target, but we have a distorted representation of the target. That means that if we have a quite complex scenario, the image that we have with at the end of a GPR service is a quite complex representation of the scenario. That is a complex representation of hyperbola. So it is necessary to process the data, the collected data, trying to obtain some focused image that provide a better representation of the scenario. This is in our institute, or what we have done in the HERACLES project is just to process the data by using a microwave tomography approach that exploits the Born approximation. I don't want to go in depth on this mathematical part, just to say that the data are related to the electromagnetic features of the area that we are investigating by means of an integral operator, and by processing the data in this way, we can obtain, as I said, focused image that provides a better representation of our scenario. This is the example that I show you first. This is the radargram on the right, and this is the microwave tomography image that we obtained for the same scenario. Okay, just to move to the some results obtained in the framework of the HERACLES project, we used the GPR only in Gubbio, at both the Gubbio test sites of the project, that are the Consoli Palace and the medieval walls. In the Consoli Palace, we used two kinds of GPR. A GPR working at high frequency with a antenna that have a nominal central frequency of 2 GHz, and a low frequency GPR system that works with a dual frequency antenna and is capable to collect at the same time data at the central frequency of 200 MHz and data with the central frequency of 600 MHz. This second kind of the GPR system was used to inspect the floor of the Consoli Palace to obtain information about its about the structure of the fundament of the palace, while the high-frequency GPR system was used for the vertical structure. In particular, we inspected a wall that is located in the loggia of the Consoli Palace. That is this part. I don't know if you are able. Okay, if this is a part where there is the senior the level 4, and in this part there is a visible and quite a significant crack, and it was the same place where the University of Perugia closed an accelerometer sensor to monitor in time the displacement of the crack. Well, I start with the results that we obtained on this crack. This is the tomographic, reported the tomographic image obtained at the end of the GPR survey. Here we collected the data along several measurement lines spaced more or less of 5 centimeters, if I remember well. And what we see are the image that we obtained at different depth, starting from the visible part of the wall, moving inside the wall, so in this direction. And so we have that the first image that is like a picture of the wall. Then moving inside, we can see that appears this crack and the more important cracks that are in red in the first image still appears, while in the third image these cracks disappear, and this allowed us to provide to obtain information about the depth of these voids, and also information that the crack that is appears in the surface, this part. I don't know if maybe with the pointer, I don't know if that part is not anymore visible. That just allow us to say, okay, the crack that we can observe in the in surface is not so deep. Another interesting information was that we had at a depth of 50 centimeters, where appears 3 localized anomaly that was interpreted as the end of the first block of stones. This means that we can see by the picture of the wall that we have 2 kinds of stones, so some big stones and some smaller one. And in the building during the construction of the wall, the big stones were connected with the small one, like a structure, a cross structure, like in this way. So we have some information about the constructive modality of this particular wall. Also, it is interesting to observe the last image that is at the depth of 70 centimeters, where we can observe that more or less half of the investigated domain is homogeneous, while in the second half part we have some anomaly. This is because the thickness of the 2 walls are completely different. The wall made with small stones is finished after we have a room, while the wall that is made with big stones, that is a perimeter wall, is containing a larger thickness. So we have in an homogeneous part from one side, from an half part of the investigated domain, while in the other side we have the hand, the back. We are seeing the back of the wall. The second result that we obtained at the Google sites regards a room located at the level -2. It is let me say the first level of the wall, the deeper one, and the result that I show in this slide is obtained by processing the data with the central frequency of 600 megahertz. In this case, we was able to detect a metallic grid that was put below the floor during a restoration period, and whose information was completely lost. Thanks to the tomographic image, we was able to estimate that the grid is again made by a cross structure of for construction materials, but also had an estimation of the size of the square that was more or less 9 centimeters. So we obtained information also on what kind of grid was used in its structure. Moreover, appears some localized anomaly that correspond to some water hole, some structure to connect the sorry to constrain the water because on the lateral wall that we can see in this picture, there are some ancient WC, some ancient toilet. So to conclude, we also use the GPS system to in the area of the medieval walls. In that case, the aim of the survey was to obtain information about the structure of the soil, because the medieval walls of Gubbio are affected by ground accumulation. So we wanted to obtain some information about the stratigraphy of the soil. Here there are some pictures of the investigated area, and this is a results obtained by process just by showing the raw data. Just we made some filtering procedure collected with the antenna 200 megahertz. In this case, we was interested to detect the material interface, so some objects that are whose size is larger than the probing wavelength, so it's not useful to apply a tomographic approach. And we also detect in this case the presence of several interfaces. 3 of them are extending along the entire trace, and 2 of them that are outlined with the dashed red line are present only in a portion of the soil that can be represented that in the different part of the trace, the soil had a different process of accumulation. So we have that in some part it's quite homogeneous, while in another part it is there is some inhomogeneities, and this is different from the what happened in the from 3 meters until the end. That means that we have 3 layers at 0.4 meters, another at more or less 0.5 meters, and the third one at more or less 0.7 meters. But while in the first 3 meters we have only 2 interfaces. That means that here the first layer of the soil is quite homogeneous. But this does not happen from T-meters and until the end. So to conclude, the GPR is just a flexible and portable electromagnetic sensing device that can be useful in different applicative fields. The output of the GPR survey provides a distorted representation of the scenario, so sometimes it is necessary to process the data. And in the framework of the HERACLES project, it has been used, has been an effective tool to study both structure and subsoil. So thanks for the attention.